Alright, time for another draftphysics.com, debatephysics.com also, but can't solicit any debate or argument from any talking head on physics on the internet. Just can't find somebody who can make a counter argument to arguments, and it's just really disappointing, but that's the way science works. It's deaf and dumb. Yeah, and stupid, and irresponsible, and lazy, and sloppy, and not very good. Physics, anyway. So it doesn't have to be, right? Your patient's not going to die, kind of thing. So they can get away with a bunch of squirrely crap. Because, you're not going to watch the flowers die or something happen because of this bad science. So anyway, I will be making a response video to one of Jason Gibson's videos. He does have two channels, Math and Science, and then his channel by his name. And I can't see much difference in the videos, frankly, and I guess it's just he's just trying to do whatever you can do to get more action at his website, and frankly, he ought to do some good physics instead of this baby talk, frankly. And the audience, he doesn't make videos to any audience. He's making them so a 12-year-old watching, or a 27-year-old, or a 65-year-old, and that just doesn't work. So he's just constantly switching between being a kindergarten teacher and a college professor, and there's just no point in doing that. I assume your audience isn't completely stupid, or don't assume it, but choose one. Anyway, alright, so we're going to talk about Newton's third law mostly, and it's, people just make a mess out of it in a sense, understandably, but so it's just this idea that if there's an action in the universe and it does something, so to be an action it has to interact with something, that somehow there's this equal and opposite reaction. And that usually just comes down to some idea, like a Newton's cradle, that one thing goes in, this thing stops, and this thing goes. Now, in a sense, you could argue, well, that's not really a reaction. That's not an equal and opposite reaction. Something isn't going that way. So it's, you're just sort of arguing, okay, you can sort of just say something has motion and it gave the motion to something else. There's only one action. This has $10. It gives the $10 to this thing. Now this thing has the $10. It's a conservation of momentum argument, really. And but as a general statement, it works. Okay, action, reaction. Because there's so many circumstances where the action and reaction is just really about an expansion, compressions and then expansions, and expansions expand against something, and to be able to, for there to be an interaction, it has to expand against something, and so that's sort of what you get as an equal and opposite reaction. But you could argue that if I smash a tennis ball against a wall and then let it go, what's the reaction? I mean, if the ball leaves in one direction, if it's a brick wall. Now they're going to claim the whole Earth moved, but that's just a claim, and it's stupid. It didn't happen. Obviously, the energy isn't being used by the Earth, or the tennis ball wouldn't fly off at the same speed. If I made the thing I pushed it against lighter, and the thing I pushed it against moves, then the tennis ball isn't going to come back as fast. So obviously, so there are holes in the action-reaction kind of notion. And again, you could sort of understand that, if I plowed something into a ballistic pendulum, for example, or just have two things connect to each other, they're both going in the same direction still. They're just going slower. So again, we're arguing about, is stopping something really an equal and opposite reaction, or is that just the consequence of sharing what it has? So I guess this is what I would argue a much better understanding would be of the concept of motion, is to understand that if something. If I made a box and I put BBs in it, and they could just bounce around hitting surfaces, you'd recognize, okay, once I'm to a certain heat or whatever, it's pretty much going to stay in one place. It's just going to wobble a little bit, but it'll stay in one place because it's going to get hit going this way or that way or that way, equally. Okay. And the catch is, all right, is that we're going to have to argue that they lose half their energy every time they hit something. So, you're going to have to just think for a minute that there's some possibility that you can store energy, like nuclear or an electron inside of an atom, that you can store that energy perfectly efficiently. But anyway, so if you had a bunch of stuff heated inside of something and then you started letting some of it out in one direction, you can understand that over time everything's going to find that hole because it's bouncing off all the surfaces. So eventually it's going to find that hole and leave. And now all the surfaces aren't going to get hit evenly. Some surfaces are going to get hit more. And, obviously the side that doesn't have a hole in it is going to get hit more than the side that does have a hole in it. And so you can sort of understand that it's going to keep that direction is going to now be dominant because it gets hit more going in that direction. You're giving away stuff going that way. And the consequence is you probably still have stuff going this way if you were staying in one place. You've changed the balance. All right. So I don't know how to make it a better analogy. Well, I didn't spend a whole bunch of time thinking about how to make it a better analogy. Just something real, like an atomic circumstance or something where you could really understand that this model of interaction, okay, where you hit something, you stop moving, the something moves, and then something else is going to hit you because of that motion, and then you're going to get your motion back again, blah, blah, blah. But anyway, just the basic idea that I can just have this hole connected and I can make it go in any direction. And it just means that everything bounces around inside the hose. And so wherever direction the hose is the direction that now I'm going to have more stuff going this way than that way. And you can feel that. A hose has pressure, especially if you start turning it. And it moves exactly in the opposite direction of the direction you're letting go. All right, so with that preface, the semantics of equal and opposite doesn't really matter too much. The idea that you're kind of to have to conserve momentum, I would argue, is the real value of the statement, is that you can recognize that for every action there's going to be a world that contains, okay, all of the elements that were previous there. You can't make them go away. The force and the matter can't be destroyed, so you have to basically state that you're going to be able to find just as much force in the after that was in the before. All right, so let's play a video. Yeah. Hit the button. Okay, there it is. And hopefully we have reasonable volume. Maybe. Yeah, we'll see. This has to go higher, I believe. Okay. Let's try it now. Sorry.
Hello, welcome back. The title of this lesson is called Newton's Third Law of Motion, and this is part 1. So this is truly one of the most misunderstood laws in all of physics. Most people have heard of this. It's the one involving action and reaction forces. And most people probably feel like they understand it, but actually there's a couple of little things you have to really pay attention to. Otherwise you don't understand what this law is saying at all. So what we have to do is...
You can't create energy and you can't create matter. So if you just understand those two things, there's not really going to be a lot of a problem. I shouldn't say you can't create matter, because we're going to sort of argue that, frankly, force is material. I'm going to argue that it does have mass. Obviously you can reduce the mass of an atom and fly off little pieces. electrons and protons, but you can't take away the fact that there's a certain number of electrons and protons, and that's indestructible.
Understand it, write it down, draw lots of pictures, and really understand in our bones what it's telling us so that we can solve our problems.
So he doesn't draw that many pictures, doesn't use that many examples, so I'd say blah, 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 blah. Not so much.
So the first thing you have to understand is we have to analyze a little more deeply what a force is anyway. And you have to recognize in the beginning, and this is something that's not really like brought into focus until a little later in physics, but you have to recognize that anytime you have a force, any force you can think of, it's always some sort of interaction between two objects.
So it really isn't, in the sense that you could argue that, like I said, a degrading nuclear atom, an isotope, a radioactive isotope, you could argue that yes, there's a cause, but the effect is dramatically unrelated to the cause. I mean, the effect is a chain reaction inside the atom that causes all kinds of events to take place. So it would be kind of silly to say that the entire event of the nuclear decay was an opposite reaction to whatever initiated it. It's like you could take a little boulder and knock it off a mountain, and it's got a whole bunch of set up energy in it, and a whole bunch of stuff is going to happen. And to say that it's an equal reaction to poking the boulder would be silly. To say the avalanche is the opposite reaction to an extra snowflake landing on the snow pile, it would be kind of silly.
I challenge you to think and try to come up with a force that doesn't involve two objects, right? And you won't be able to do it, because anytime we have a force, by definition...
So again, it's, we don't by definition, I would argue we're all being bombarded by force constantly, and absorbed and emitted. So we're constantly involved in the universe and producing, and electrons are doing this constantly, in atoms. They're moving, and every time they do this, they push on the force, and every time they do this, they expand the force. So they're changing the frequency of the radiation in the universe all the time.
There always has to be two objects interacting with each other. Let me give you some examples. The Earth interacts gravitationally and pulls on the moon.
All right, so it doesn't pull on the moon. It obviously, I would say it's kind of obvious once you think about it a little while. The Earth is absorbing force coming from the external universe, and that absorption is essentially a shadow. It's casting a shadow on the moon. So there's less motion, there's less stuff hitting the moon from one side than the other, so it gets pushed into the Earth.
But the moon has gravity also, and it interacts and pulls on the Earth.
Yes, it casts a very small shadow.
So you see, there's two objects involved.
No, it's not that much smaller, right? 1/6 the size or something. It's still pretty big.
In the forces that are going on there. When I push on this board, my hand is in contact with the board. I'm pushing on the board. But
so he's talking about pushing on the board, but the idea is the actual fact is the board isn't doing anything. So the board is not moving. So you're applying a force, but the board isn't absorbing it. So to say there's a force going into the board is just you saying so, because there's no evidence that a force is going into the board. So there's, and your action is obviously being, stopped. So if you threw a ball at the board, then you have to explain either the ball is going to reflect, or the ball is going to compress, or the ball is going to break the wall, or the wall is going to move. But those are your four choices.
you see, there's another body involved, the board itself. There's two bodies involved anytime there's a force. If I have a rope and I pull...
Obviously, the only time it's relevant is the force has to interact with something. So you could say anytime there's a force, there's two bodies involved. When there's not, there's the force and the thing it's hitting. So photons hitting a surface, and, they're ultraviolet ones, and they cause, all kinds of ionization and start breaking all kinds of atoms.
Pull on a rope tied to a car or something. I'm pulling on the rope.
You're actually pushing on the rope. The actual physics is that you're pushing on the rope. You're grabbing, you're creating friction, and you're pushing. You're not pulling. You're pushing on the electrons in the opposite direction of what you want to. You want the illusion of a pull, but that's all it is the illusion of a pull. The actual fact is it's a push.
But you see, the rope is attached to my hand. There's always two objects anytime there's a force.
So I don't. There's just no point in saying there's always two objects anytime there's a force, because there isn't always two objects. Again, photons coming billions of light years through space. Are you going to say that the other object is the one that produced the force? Well, obviously everything has a history. So if you're going to say that you can't have an interaction unless one thing has a history of producing a force, well then yeah, because that's the only way two things can hit each other.
Electric and magnetic forces, where you have an electron over here and a proton here, and they're attracting each other. You see what's going on?
Okay, so they're really not attracting, they're being pushed into each other. But anyway,
going on, there's two bodies. Anytime there's an attractive force or a repulsion force, there's always two bodies. So I challenge.
All right, so I still just don't get it, because obviously the electromagnetic radiation that can affect us can travel zillions of light years through space, and it would just be silly to talk about the source of the cosmic rays or something.
You again to try to think of any situation where there's forces going on and try to find one where there's only one body. You won't be able to do it. If I flap my arms, like this, well, one of the bodies is my hand, and the other object is the air surrounding my hand.
So I would just have the same challenge to him. I'd say, give me the example of a real pull. Something that's a real pull, a real physical pull. Show me. And now I'll argue that, no, you can always figure out how it's a push.
So the reason I'm setting the lesson up like this is because I want you to have it in your mind that any time you interact with a force, or that you can imagine a force.
No offense, but if you're...
So he keeps saying it as if the only way to imagine a force is when it's on a material object, but not all the forces are being carried by something material. So it doesn't really work. So we just said it always involved
two bodies, always. So then when you recognize that, then you understand a little bit more why Newton's law of motion, third law of motion, makes sense. So I'm going to say it out loud, and then I'm going to draw a lot of examples on the board.
So it makes sense because of symmetry, generally speaking. So I'm just saying, like, the bullet exploding is the explosion. The idea of a expansion and contraction is always going to be it creates an obvious symmetry. And so you could argue that that's the rudimentary way of understanding an action and reaction. But lots of examples aren't expansions or contractions.
I'm also going to write it on the board because this one's important enough we need to write it. And Newton's third law basically says the following: to every action force, there is an equal and opposite reaction force.
Okay, so he's rewording it. And if force is just momentum, so again, you could argue that any change in momentum comes with a change in momentum. So the change in momentum for the circumstance, if you change something's momentum, there's something else that's had its momentum changed equally. So you can always find a change in momentum. So that might be a better way to word it. Now, it's unfortunate that Newton wrote this crap in Latin. Originally. I don't know why an English-speaking person in England would bother thinking that that's more scientific, because as obviously you can see from a lot of translations, they're translated all different. They're using different words. It's just a fact. It doesn't translate perfectly. So, yeah, it's just damn unfortunate that he didn't write it in English.
Sounds simple, right? But why is there an equal and opposite reaction force?
It's unfortunate he didn't translate his own work. in English. You know, if you go ahead, publish the Latin version, but publish the English version. And then we'll all know what you really meant. You know, no, didn't do it.
The main reason is because anytime you have a force, there's always two bodies involved. So you can't just have a one-sided force acting because there's...
So I don't know why he thinks this is so important. And again, you're really just saying some kind of action that we can see or something. You know, it needs to be matter. But I'm just sitting here stuck with the idea that there's not two bodies involved in something like photons hitting you.
There's always two bodies interacting. There's always going to be some force reacting backwards in the backwards direction on the other body. That is why Newton's law says that for every...
So obviously the light bulb is not being disturbed by anything that's happening to me. So there's no equal and opposite effect on a light bulb. The light bulb shoots the force at me, the force hits me, it scatters all over the place. You know, the light bulb doesn't get the equal and opposite reaction. The universe gets the equal and opposite reaction.
Action, there's an equal and opposite reaction because for every force you can imagine, and I just gave you 5 examples, there's...
So the simple principle is you can shoot, let's say I made it a laser beam instead of a light bulb, and I can put the electricity in. I can say there's a certain amount of watts, and a certain amount of watts are going to hit me, minus whatever amount get wasted as heat. But again, it's more of a conservation law than some statement about this equal and opposite crap. It's just saying you have to conserve the force, the momentum.
There's always two bodies. So that's the fundamental reason. And the other thing I'll say out loud, we will also write it on the board, is that these two forces, they occur in pairs, action and reaction. They never act...
All right, so there's no reaction force. There's a reaction event. Okay, so the simple argument is, again, if I have $10 and I give it away, I don't need some criminal to come and take my $10 from me. I already gave it away. There's no force that takes my $10. I gave it to something. So in a Newton's cradle, there's no counter force that stops the one ball from moving. The counter force is its own, I gave it away. I don't have it anymore because I gave it to the other ball. It's gone. I don't have it anymore. The stuff, the force I had, is now in it. Ugh.
On the same body. They always act on the two bodies that are present in the interaction. So for instance, my hand pushes on the board.
So again, he's saying he just pushed on the board, that he just did something to the board. He didn't do anything to the board. The board is not changed.
That is a force from my hand into the board. But the board pushes back into my hand, and that force acts on my hand.
No. So actually the board doesn't accept the energy, and so therefore it just gives it back. So if I bang the Newtons, if I make the Newton's cradle so it can't move, that is, I make it like an anvil, then the ball that comes in just bounces back. That's it. It just reflects. There's nothing going that way, and now it's going that way because it changed the direction, because it just rejected it. There's no equal and opposite. There's just conservation of the motion. You had a certain amount of momentum in, you have a certain amount of momentum out, and that's it. You can't heat this, you can't move this, you can't do anything to this if you get the same motion out. If you get the same momentum coming back out of something, then you didn't leave anything inside of the something.
So you see, the first force is me acting on the board, and the other reaction force is the board pushing into my hand.
Right, so the board doesn't push into your hand. It just says, I'm not moving. That's not the same thing as it doing something or it providing a force. It's just you feeling your own force because it's rejecting it, saying, I'm not accepting it. Push all you want, you're just pushing against yourself. It's giving you the mirror image of your action. but it absorbs nothing, okay, or you lose the energy to heat or something else.
Both of those forces, they act on different objects. The first force acts on the board, and the reaction force acts on my hand.
So it just doesn't happen that way. There's no reaction force. There's just momentum applied, and it either moves the object and is absorbed, or it's partially absorbed and partially reflected. But you can't have both. You can't throw it, hit it, move the object, and get your energy all back again. You can't do that.
They do not act on the same body. If you think you have an action-reaction pair that acts on the same body, you're wrong, because it can't by definition.
So I don't even know how to imagine if you have an action and reaction pair that isn't a pair. No, I can't do that.
These forces, the action and the reaction forces, they always happens between pair of objects that are interacting, and they always act on different bodies.
So whatever. So we know we don't need objects. We just need a force and a material body to act on, to have an action and a reaction.
So let's draw some pictures and get a lot of examples, and then I'll write Newton's third law on the board out as well.
Well, who cares? I mean, that's just a waste of everybody's time. What we're arguing is what's the true mechanics of motion. And the simple argument I'd make is that it's just about momentum. There's a certain amount of mass in the universe, and it has a certain amount of velocity. And so I could just add it all up, and that quantity is conserved. Now you have to understand that the catch is the force. The photons are made out of little bits that have mass. Force is mass. It conveys momentum. And the fact is that what you can do to the force is change its velocity. So if a little bit of force with a tiny mass hits me and becomes part of me, then my mass is now bigger, and that velocity is spread over my gigantic mass. And that's what really happens. So you're conserving the mv. I have a much slower velocity now, and so you can understand though, but the total is still conserved.
And so
the total amount of motion in the universe. So again, this is 350, 400 years ago. This is Descartesian physics, and you still have to argue it. Descartes was correct. There's a certain amount of motion in the universe, a heat, you want to call it, and that's it. And all it can do is go from one object to another object to another object. It can be exchanged between objects, but there's always the same amount of the key element called motion. The quantity of motion is always the same.
You can, by the end of this, understand exactly what's going on. So here you get to experience my drawing skills, because here I'm going to draw.
And the catch is when you get to the nuclear thing, there's a whole strong force is where everything goes to the funny part. Where it doesn't take as much energy to push an electron between two protons as you're going to get back. And the fact that if you remove that electron with the two protons now very close to each other, that you're going to get a lot more energy back than you put in.
A ball, right? So here we go, ball, like this. And then I'm going to draw a foot kicking this ball.
So these are the only examples we're going to get is foot kicking ball and then bat hitting ball. We're not going to, so that's as far as the examples go. So we're not going to get gun with bullets in it, and if I put two bullets in, what happens? We're not going to get spring and ball against wall, and I push the spring and the wall doesn't move and the spring expands and the ball shoots off at a different velocity than if the wall did move. Fact.
I'm a terrible artist. You all know this. So here is a foot, something like this. And it's kicking the ball. It's not
something like a Dutch foot.
Not just sitting here. It's like wham, hits the ball.
Looks like it would wear a wooden shoe.
Like this. So what happens at the instant of time? that we're interested in. Well, what happens is there is a force, so just forget about the foot. The foot kicks it, but just forget about it. There is a force that acts on this ball. It goes this way. And you could call it F, but to talk about more specifically what's happening, this is the foot.
I love it so much.
Yeah. All right, should be back. So the obviously connecting a foot to a leg to to a torso, it's very complicated. So if you just said, okay, you have a mass, okay, called foot, and it's going to hit a ball, so it has a mass and a velocity, then you can do this. But if I am allowed to imagine the entire person and all the different torques that are going to be applied, then it's not just about a foot that has a momentum. And it's really just better to understand this is about momentum being conserved. You don't need to do that. You need to do this. Well, I'll do that and then this. All right, so back to this. So this example is more complicated than... Obviously, we know that you have to have a peak velocity when you're going to make contact with the ball, and that's really all you can do, is your foot has to be going fast enough to push the ball and then have the ball, whatever elasticity it has, flexibility, do a little expanding and add a little bit more velocity. So you can use the example of a golf, the head of a driver hitting a ball. And the mass of the head matters, but it doesn't, the real important fact is that you need to be at a peak velocity when you hit the ball, because the only way you can give the ball velocity is to exchange it with you, and you're only going to be able to move that club head a certain speed, a maximum speed. And the key thing is you need to hit it at the right time where you're moving your foot, in this case, at its maximum speed. So you have to try to get yourself almost airborne and falling backwards when you hit the ball. So you have created the maximum velocity in your foot. But anyway, continuing.
And that's because I've drawn the arrow from the ball. Now, of course, the force comes from my foot, but ultimately...
So obviously we could just cut your foot off and just say, okay, we're throwing a foot at a ball. Let's just understand it as an MV argument. And then understand that when the foot hits the ball, if it's elastic, right, there's going to be a certain amount of contact time. But there's going to be a point where your foot is still moving and the ball is moving much faster than your foot. You've lost your peak velocity, and the ball you're not even in contact with it anymore. And so all of this extra motion, the foot is going to keep moving. There's going to be a lot of energy that you're not able to put into the ball. So only a portion of the MV of the foot is going to be put into the ball. And, in a way, the faster you hit the ball, the more energy you won't put in, you'll retain. So you keep losing energy as you try to kick it faster and faster. Your efficiency at exchanging gets less and less. And so the heavier the ball is, and the slower it's going to go, the more efficiently you'll be able to get your energy into it. Just a fact.
It's impacting this thing, and the force that's acting on this thing is in this direction, and it's because of my foot acting on the ball. Now, what Newton's third law is saying is that at the moment...
So what the third law is just saying is the force, the momentum. Force is momentum. Twice the force, twice the velocity. 3 times the force, 3 times the velocity. That's what he says right under the second law, demonstrating that he understands them to be the same thing. So it's just about momentum in and total momentum out.
Of contact, you see, as we said for many, many examples, there's always two bodies interacting between when there's a force. You cannot come up with a situation where there's a force happening and only one body. You can't have just like a force acting on itself. It never happened.
It's not about a force acting on itself. It's about a force acting on an object. So again, this comes down to, he's making the argument that we're only going to talk about forces that are contained by material objects. So we're just not talking about forces like magnetism or photons or other even moving electrons. I don't know whether he counts that as matter or force, but regardless, he's making a distinction. He's saying the force isn't something matter carries. He's saying that, it's hard to say what he's, again, I've always elementally understood that the force is this invisible speed of light stuff, and the motion happens, the stuff we see has to have matter involved because we can't see force against force. And we don't see it. This is more critical. We don't see laser beams crash into laser beams. So force doesn't interact until it moves a piece of matter.
So in this case, the two bodies are the foot and the ball. So when I kick the ball, I impart a force from the foot onto the ball.
Right. The force has something, though, the velocity, and it got it through the same process of interactions inside your body. So a bunch of elastic interactions created the motion in the foot in the first place. And you're just saying, again, you have to conserve the motion, which is the same thing as saying conserve the energy.
But at that moment of contact, then there is also a reaction force. That is a force, I'll call it capital F. I'll put my little vectors on top here.
So there really isn't. You can tell, look, you kick a light ball that doesn't weigh much. It's really easy. You don't feel a thing. Kick a heavy ball that, is hard and heavy. You're going to feel a lot. And it's just because it's a lot more work you have to put in to make it move. But if it moves freely, all you're doing is exchanging. You're taking what you have and you're putting it into the object. So, I can hit a pretty hard object with a hammer, and I can make it move, and it doesn't feel like I did any work. The work I did was to move the hammer. The work I did wasn't when I hit the ball, my hammer, vibrated and broke my arm off. None of that happened. So there was the action force, and I'm not going to notice any reaction force if I win. That is, if I move the object. If the object doesn't move, then I'm going to feel my own force thrown back in my face.
Which is the ball acting on.
You kick a brick wall, right? What are you going to feel? You're going to feel your own energy returning to you. Okay? That's it. You're getting a U-turn of what you put in. It's a mirror. Hard, big things are essentially a force mirror. Whatever you throw at them, they're going to bounce off and throw it back at you.
The foot. This is an action-reaction pair.
It's just as you can look, I go to use Professor Lewin's tomato example, right? Okay, so I have a tomato and a baseball. They weigh the same, let's just say. And I throw them at your face. Obviously, the tomato got the same force as the baseball. I'm throwing them at the same speed. But obviously, your face is going to react completely different to the two events. And in one event, you're going to splatter a bunch of water molecules all over the place and reflect them. In the other case, you're not going to get much reflection, and you're going to get a baseball hole or dent in your face.
All right. Now, the first thing you're probably thinking is, well, I've never felt a ball kick my foot. That isn't real. But think about it for a second.
Yeah, no, think about it for a second. You really haven't, okay? It's nothing like the force you gave the ball. You're not feeling anything like that because the ball's yielding and moving. Kick a brick wall, and then you'll feel the force that you actually were hitting the ball with. You'll feel the real momentum of your kick. So that it'll be a real equal and opposite reaction. Okay, so kick a brick wall, and then you'll feel the real equal and opposite reaction.
Just imagine a little soccer ball that gives a little bit. And when you give it a nice swift kick, you probably have felt the compression of that ball.
Right, and it's not just the compression of the ball, right? So the ball stops compressing. Let's just say your foot hits, the ball starts to compress, but you're still moving the ball. So it's like kicking a spring. you're giving the spring some momentum, and then the spring's going to expand and give you a little extra momentum.
And if you kick it at just the right, you can't see my feet here, so just imagine this is my foot.
I mean, this is all stuff happens in milliseconds, little portions of a second. And the dynamics are really just about electrons. And it's about atoms, elastic atoms. So, and the trick is that the atoms in a steel ball are more consistently elastic than a rubber ball. Because in a rubber ball, it's actually atoms, the whole atoms are moving. Where in the steel ball, it's just the pressure of the electrons.
It kicks the ball. I'm sure you've had that situation where your foot has rebounded off of the ball.
No, I haven't, so. No. That's why everybody has a follow-through, okay? Nobody hits a golf ball and the club flies backwards. It just doesn't happen. So I think it's a really poor example. Okay, that's all I'll say. Nobody's hit a baseball and the bat flew backwards, and none of these examples are going to work.
That is the force of that ball kind of kicking your foot back.
No, that's when you go into it with too little momentum, and then you're going to sit there and run out of fuel, so to speak. But that's the only way it could happen. You can't have a reflection and put the energy into the object. That you can't do.
You have a microscopic...
a full reflection. I shouldn't say that. You can put part of the energy in and get part of it back. But most of these cases, to put the energy in, you have to have so much more momentum than you're going to actually put into the object that all the extra is going to create a follow-through. I'm just trying to think of some example. He's providing examples, and where you have that, where you have enough of a reaction, that is enough of a reflection, to actually not have a follow-through.
Compression of that ball, which deforms the ball, and that increases the pressure in the ball, and when it springs back, it pushes right back onto your foot.
Right, but not with anything like the same energy you put in.
So if you kick it at just the right moment, you can feel it kind of kick your foot back. So the ball moves in its direction, and the foot moves backwards in its direction.
Right, so that we know this doesn't happen, okay? There's just no examples of anybody ever having their foot go backwards unless they hit a ball that's a brick wall. I mean, unless it's a cement ball they're kicking, it just doesn't happen.
Because I've imparted a force on the ball moves that way, and the force back onto my foot makes my foot kind of rebound that way. You can think of those little balls, tick, 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 those little things.
So that's how he describes Newton's cradle. Anyway, and how is that a good example of this? I mean, obviously it's a complete transfer. The ball doesn't bounce. It doesn't hit the other ball and they both move. It's a complete transfer. There's no reaction backwards.
Things that do this, right? Sort of kind of the same thing. Or you can imagine...
So we know it's sort of not exactly opposite thing in the sense that you made a complete transfer.
Holding one still and it bounces off like this. So it's the same sort of...
Yes, right. And that one bounces off. Why? Because the energy went into the object? No, because the momentum wasn't transferred. Clearly, the ball bounces back more the less the wall moves. The more the wall moves, the less the ball bounces back. I mean, their physics is so rotten. I mean, I wish he got into mv squared here, but I mean, he's still talking as if you can put twice the force into the wall and get back everything. Get back all of your energy. Swing the pendulum all the way back up again to hit again. And put twice the energy into the wall. And then swing it back and get all your energy and do it again. And put and then put twice the energy into the wall. That's what their physics says happens. And it's idiotic.
The reaction force is present because there's always two objects interacting with a force. Now, the important thing that I said verbally that we're going to write down also is that action reaction.
Let's just say you can't have an interaction unless there's two things interacting, right? There's a minimum action rule, which is where you can't have an interaction unless there's more than one thing. I mean, that just seems a reasonable statement, right? Interaction requires two things, at least at minimum. Can't have an interaction with one thing.
Action pairs of forces, they never cancel. You can never just cancel. It's easy to think that...
So that's what they say, and yet that's not what they believe or they're preaching. They're saying that if your foot goes backwards, it means more energy went into the object. That's their physics. They actually believe that. The more energy goes back this way, the more that reflects, means even more energy went into the object.
Oh, this one is in this direction and this one is in this direction. They're going to cancel because they're...
So you can have 100 in and you can get 300 out. 100 going this way and 200 going that way. That's their theory. yeah, it's really bad.
Equal and opposite, so there's nothing happening. But that's not true, because this force is acting on the ball, but this force is acting on the foot.
So again, there's no extra force. The MV exists, and the MV ends up out. And the fact is that the MV went in, and it got rejected and got thrown back the other way. That's all that happened.
These forces act on different objects. And so the only way you could cancel something is if you had multiple forces acting like on the same object. But these forces, we need your...
And again, they don't really cancel. If you turn the steering wheel left, it really happens. And then when you turn it back right again, that really happens. They're real events. They take real energies can be followed. There's no cancellation. All these damn commercials. Yeah, I'm just going to say for the sake of it, there's all these really racist and horrible commercials on YouTube. I don't know how they get away with it. I'm just surprised that there's no uproar. I actually saw someone where a black guy was saying white doctors are lying to us, and we don't have diabetes and we don't have this, and because we have super black blood. I mean, it was so freaking bad. I mean, if they put white people on talking that kind of shit, everybody, every highway in America would be covered in burning cars. I mean, it was so bad. And you're just saying, what the fuck is going on that this crap is allowed? I mean, they're selling these cures for cancer, all kinds of this pink salt shit, all kinds of lies. What the fuck is going on? I mean, where how low are the standards going to go? It's just so fucking bad. I mean, it's this isn't snake oil. This is outright just poison, being sold. And it's just, it's scary shit what's going on. It just really is too stupid. You're saying, no, this world can't get this stupid, but it just keeps getting more and more idiocracy. It just keeps getting dumber and dumber.
They don't act on the same object. They act always on two different objects. So if you're solving a physics problem and you're coming up with an action and a reaction force and you're trying to put them and act on the same body, you've immediately made a mistake.
So it's just silly acting on the same body, because we know if I bounce the steel ball on the anvil, the only thing that's ever going to be moving is that steel ball. The anvil ain't moving, the earth ain't moving, nothing else is MVing. The only thing MVing is the goddamn ball.
Because they never act on the same body. Ever, 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 ever.
I don't even know what that means. It's just ridiculous. There's no point in asserting it. Who cares? It's about conservation of motion. Quantity of motion, conservation of the quantity of motion, and that's all you have to worry about is the MV. Follow the MV and you're done.
So what I want to do next I'm going to write one more example under here.
I mean, this all comes back again to the lever paradox, this whole bullshit that somehow these people believe that I can, if you understand that friction is just like little pieces in the ground, like bowling pins, and they're moving. So when you're, rolling something and it's slowing down because of friction, it's because it's moving the pins. So it can't keep its momentum and move the pins is the simple principle. You can't roll a bowling ball, knock down all the pins, and the bowling ball still goes with the same momentum. It has to use the momentum to cause something else to move. So you can't make heat without using momentum. So obviously you can't conserve all your momentum, ballistic pendulum. You can't have all the momentum go into the pendulum, move it, and then claim that 90% or 99.4% of the energy made heat, because you don't have any momentum to make the heat with. Because you conserved it all. The bowling ball is still moving the same speed. You can't say the bowling ball is still moving the same speed and I knocked down all the pins. Can't do both. And that's how dumb their physics is. And again, I don't, even saying this stuff, their theory says it takes 25 times the energy, the fuel, to go 5 times as fast. You've never experienced that in your life. Okay, there's no example of that being true. Spinning a drill or anything, a mixer in your house to make the mixing blades go 5 times faster. You don't use 25 times the electricity. It's ridiculous nonsense. And here I have to make these videos. Shit. It's scary. This guy worked at NASA and he hasn't figured that out, that 25 times sounds ludicrous and idiotic. It doesn't take 25 times the electricity to spin a motor 5 times as fast. Why do people believe that shit? Why are they preaching that shit? That's just too stupid. Really, I mean, every fucking... what can you say? I mean, you're just saying it, right? Their theory says that's true. It takes 100 times the energy to go 10 times as fast. That's what their theory says. And you know it's not true.
And then we're going to write Newton's third law down. Then we're going to draw a bunch of different examples like this. The only way you can really get the feel for action and
There's not a bunch of examples.
reaction is to see a bunch of examples. So here is a butterfly.
I mean, you could do the rocket example, right? And if you don't, if you think about it as expelling something like heat, then you don't really have two objects.
Flapping its wings.
So this is just a terrible, again, example because it's too complicated. We know that the whole lift of airplanes and butterflies is all way too complicated to use as a Newtonian example. I mean, it's not simple enough.
And I already mentioned this one verbally, but let's just do it. Now again, I can't draw, you know this. So this is a wing of a butterfly, and looks like my marker's almost out of ink. Here's another wing of a butterfly. I'll try to clean this up. Use your imagination. That's a butterfly, okay? You have 2 little antennae like this, right? So you can tell I'm a terrible artist. That's okay. So what you have here is the butterfly doing its thing like this, right? Okay. So what happens is you have a force.
So we know that doing its thing is not just that simple. We know it flaps this way and then pushes down. I mean, it does a whole bunch of complicated motions.
Acting down like this, which is going to be the force of the wing on air.
Right, and so it has to push down faster than it lifts up, right? Or else it would just stay in one place, wouldn't it? Yes.
So when you push down, there is a force of you pushing the air down. What would the reaction force be? It would be an upward force, which would be...
All right, so there's no upward force. You're just wrong again. It's just wrong to state it that way. What you're doing is creating a vacuum, essentially, a density vacuum above the wing. So when you push the air down, you obviously have a bunch of air molecules now that have to fill the void you left behind. So there's a bunch of compressed air below the wing, and there's a bunch of trying to make a vacuum, and nature abhors a vacuum kind of argument. I mean, the simple argument is you can't have a vacuum. You can't create a vacuum in this dense atmosphere. So obviously there's going to be less density of molecules and therefore less pressure hitting your wing, because the air molecules are going to be very busy filling the void left behind by the wing. I mean, that's sort of what lifts the airplane, right? Is the wing. The air is going, the air is moving faster because you're basically creating a vacuum of air. There's an absence of air, at the very end of the top of the wing, and that's what's lifting you up.
F of the air acting on the wing. I really want you to think about this for a second. The wing is acting on the air is acting on the...
So it's just, like I said, this is there's so many subtleties in this whole fluid dynamic argument. So, yes, stick to Newton's cradles and such.
The wing. Notice that these forces can't cancel because they don't act on the same thing. This is a force on the air, and this is a force on the wing. Those forces are...
So, okay, so he's saying there's a force on the wing, but he doesn't describe it as anything other than, obviously you're creating a higher density of air below the wing. And so you're creating less dense air above the wing. That's a fact.
Are acting on totally different objects. So what happens is when you push down, you're pushing and you impart a force on the air. That force moves the air down. But at the moment of that force happening, the force of there is a reaction force where the air is pushing up on...
All right, says you, and again, the key factors is which one's causing the effect, the reduced pressure above or the increased pressure below. Yeah, so which one really is doing it?
Your wing, and that is how you kind of maintain your little altitude. Without the reaction force, which actually is acting on your wing, then of course flapping wouldn't do anything. So you're simultaneously pushing the air down.
It's a buoyancy thing, right? So the real argument is that you're being lifted in the atmosphere because you're becoming more buoyant. So it's just... Yeah, this is just too messy an example.
Down while the air is pushing your hand or your wings up. All right, so that is our second little example. Now what we want to do is write down Newton's third law so we can get it on the board before I lose you here.
Boy, I could skip all of that. Let's skip all of that.
Third law.
All right, so he just wasted time writing this on the board, which I just, for the life of me, can't understand why somebody would do that. Write it ahead of time and show it to everybody. I don't, but who cares? You already stated it. What are you going to write it for? But anyway, so he just says, if I was as smart as Isaac Newton, you wouldn't be writing this crap.
I would say to every action force, there is an equal and opposite reaction force that act on different objects.
So no point in saying it, frankly, like I said, because the action force is often just that, a force. There's no way the force is going to react. It's either going to be absorbed or it's going to be reflected. It's either going to be absorbed or it's going to be reflected. It's only two choices.
Or on the partner object.
Are partially absorbed and partially reflected, of course. But that's all. All that can happen is it either goes into something or it doesn't go in. But those are the two options.
In the interaction. Because it makes it sound like there's always two forces and they just cancel. Equal and opposite cancel. But that's not what's happening.
Right. That's, of course, the canceling argument is stupid. And the direction argument is stupid. That somehow directional momentum matters. Because it's really stupid to say that a nuclear bomb doesn't have any momentum or energy in it because there's pieces going this way and pieces going that way and they all cancel each other and therefore there's no action happening. There's no event. Because there's no momentum. There's zero momentum before the explosion and zero momentum after the explosion. I mean, it's just too fucking ridiculous.
The forces are acting on totally different things. All right? So, there. Now, the way you would mathematically write that is you would basically say some force of object A acting on object B is going to be equal to the negative of the force of object B acting on A. Now we get a little bit.
Yeah, it's just silly. B minus A equals A minus B. I mean, it's just a waste of time.
Mathematical, and a lot of people's brains start to blow up. What does this mean? This means the force of my foot acting on the ball is exactly the same thing as the force acting from the ball acting on my foot.
So again, obviously we could make these relativity arguments that, it's very hard to tell which object's actually moving in any interaction. Because we can't see their absolute, vectors of momentum. And so if they share some vector of momentum, it's irrelevant to the differences between them. So they'll be equal things if they're doing the same thing, and then they can have some inequality in an interaction. But you can't have an interaction until you have two things that obviously aren't flying in parallel. They're flying in some circumstance that's going to make them interact. So they have to have a difference. So two things with a different momentum interact. And the simple argument is you're going to conserve the action. You'll have as much action in the real universe after the event that you had before the event. Again, it's just a conservation law more than anything else. Continuing, we better get this done.
But there's a negative sign here, which just means that it's in the exact opposite direction of whatever the direction of this force was. That's exactly what I've codified here. This force would be like in the positive direction. This force would be in the negative direction. But what?
All right, so it just doesn't happen, right? The foot hits, it can go 3/4. I mean, there's all kinds of different amounts of action and reaction. It's just wrong to say, okay, just understand it as a currency. You have $10 bills. You can give away $3. You give away 3, you still have 7. Nobody took 3 from you. You gave them away. There's no force that takes them away.
What this doesn't say, because I'm trying to kind of like beat it into your head so you don't forget it, this equation doesn't, it sort of tells you down here, but it doesn't emphasize that they're acting on totally different objects. So it looks like people...
So there's no action. Again, if I give away something, there's no counter force that took the money from me. Giving it away means I have less of something. It means I've changed. I've already changed when I gave it away. I don't need something to change me because I'm already changed.
See, they're equal and opposite. They cancel somehow, but they don't, because A and B are different objects. Foot and ball are different objects. Wing and air are different objects, and so on.
And so on. And the argument is that you can't put more momentum in the universe. So if you get it all back, if it reflects, you didn't put twice as much in. You can't make free momentum.
And then the next thing I want to write under here is a note. It's not really part of Newton's law, but it's just as important as everything we've written.
Oh, okay. So let's skip this part too, right?
With saying they never underline, 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 cancel.
Now, what would you say are some of the most important skills or qualities for somebody interested?
All right. So he says reaction forces never act on the same object. So there's no reaction force, frankly. Photons hit you. No reaction force. And they never cancel. Yes, obviously the canceling part is nonsense.
Yes, sometimes in physics, forces cancel. Sure, happens a lot.
No, it doesn't. They never cancel. They're always stuck. If two things go in and nothing comes out, then they're still in there pushing on each other. They've created pressure. They've pressurized something. And the capacity to expand still exists. Either trap it as a circle or you trap it inside a box bouncing back and forth, but you can only trap energy. You can't cancel it.
But never an action-reaction pair, ever. Never does, because they act on different objects. And we're going to get to some examples.
The examples suck.
I'm sure in your mind you're thinking, well, we've already done some examples where I think they cancel. Well, those were not action-reaction pairs. I'll get into the details in just a minute. We'll show you some examples. So let's jump. We've already done two little examples right here. Variety is the spice of life. Let's do a little bit more. Let's talk about a bat.
So I wish he was doing so the bat and the ball is the same as the foot and the ball, so that's just too useless.
And a ball.
Talk about a ballistic pendulum, absorbs a bullet. All right. It conserves most all the momentum in the linear motion of the pendulum. And yet your argument is that there's 99.94% of the kinetic energy is heat. Is still in the pendulum somewhere. So there's a bunch of stuff moving and there's no momentum conserved because all of that motion has to be free momentum.
Right, a bat and a ball. So you're standing at the mound, you crack against the bat, against the ball.
Lever example, right? I put a one mass, two distances going 1.4 the velocity in, and I get a two mass going one velocity out. Free momentum. No, doesn't happen.
What do you have? You have some bat, which is some elongated object, and you have some ball, which is some spherical object, and of course it's swinging kind of like this.
So another silly example, so I guess we'll just end the video here. I mean, frankly, we know we don't hit, nobody like except, 10-year-olds hit balls that aren't moving with a bat. So you end up with two forces interacting. And obviously when you hit a bat into a ball that's not moving, like some ball on a pedestal or something, the bat doesn't go backwards. Silly. So anyway, till the next time and such, this is not good physics. That's let me just say that, and it's not good for any age group. It's just the world's just tragically stupid. So anyway, till the next time and such and so forth and whatnot. Too stupid.